NREL. We'll wait just another minute to let people join, and then we'll go ahead and get started. I'm an engineer on the SAM team, and today I'm going to be giving an overview of SAM's new model for bifacial PV modules. I'd like to just point out that this is a series that starts a few webinars that we'll be giving over the next couple months. And so in September, we'll also be giving an introduction to some new solar resource data download features. And then in October, we'll introduce how to model PV systems with multiple MPPT inverters. And as always, our webinars are posted for free at sam.nrel.gov/webinars. And so this webinar, including the presentation, will be available there probably tomorrow. I'm sure most of you already know about SAM and what it is, but just for those that might be new, here's kind of a quick overview of SAM. To download the desktop application or the software development kit, you can go to sam.nrel.gov. And all of the open source code is posted on github.com/nrel/sam, which is kind of the gateway for a few different repositories that make up SAM. And I'd also like to mention that we'll be releasing a new public version of SAM sometime next month. And so we're just wrapping up at the addition of some new features and testing. And that's also where you can come in. So if you'd like, we have a beta release available that you can download on any platform. And we'd love to get any feedback if you find any issues or bugs or see anything that's not quite right. You can definitely reach out to us, and we will try to fix them before we release SAM. And I'll also point out that the features that I'm going to show you today are within this beta release. So if you want to test out the bifacial model, please download this and give it a try. So as part of my talk today, I'm going to be discussing just a brief introduction to bifacial PV, an overview of the bifacial irradiance model that we have implemented into SAM, some of the details of how it's been added into SAM. I'll give a quick demo, and then hopefully we'll have plenty of time for Q&A at the end. So bifacial PV, as it sounds like, is essentially the ability to capture not only the front side irradiance, but also rear side irradiance. So in a traditional monofacial PV module, you have an opaque backsheet, and you're capturing irradiance from direct irradiance, diffuse irradiance, and ground reflected irradiance on the front side. So for bifacial PV, there are a few additional manufacturing steps, and then you remove the opaque backsheet, and you can capture irradiance that is reflected from the ground and diffuse irradiance on the rear side. And so the thought is that if you can with fairly low cost or even no cost, remove the backsheet and increase the irradiance captured from the module, you can increase the net efficiency of the module and potentially lower the LCOE of PV. And so, again, that's a really quick introduction. I am by no means the first to write about bifacial PV, so please explore the literature if you'd like to get more information about that. The model that we're implementing into SAM, I'd also like to give a lot of credit to the team at NREL, University of Iowa, and Sandia National Labs, who helped develop this model. And so it's a bifacial irradiance model that calculates what the plane of array irradiance on the rear side of the module is. And so you can find that model here linked to the nrel.gov site. And there's also a Python implementation of the model on github.com/nrel that if you'd like to explore the model, just not in the SAM platform, but in a more like just Python environment, that's definitely a good place to start as well. And then the SAM implementation is open source at this link below. So I'm going to take you through the steps of this model. And I'll just point out that, again, I'm not the creator of this model, so I have implemented this model into SAM, and I can answer questions about it, but I'm not the one that has derived this model, so just keep that in mind. So the first step for the model is to identify the ground that is shaded by the PV array. And to do this, we calculate the sun position, project shadows into the row-to-row dimension, which is the area between rows of a PV array, divide the row into n segments, which we use 100 segments, and then identify whether each segment is shaded or not. Then we're going to determine the irradiance received by the ground by accounting for shading and the restricted view of the sky, and essentially use the Perez tilted surface model with the DNI and DHI to decompose the diffuse irradiance into circumsolar, sky, and horizon components. And then for each of those n segments, we're going to calculate the ground irradiance. After that, we are going to determine the irradiance for the rear side, which is going to be a sum of several components. So there will be some radiation from the sky, a limited amount of direct radiation, some diffuse radiation. A lot of the radiation on the rear side is going to be coming from the ground reflections. And then we're also going to take into account radiation reflected from the front surface of PV modules in the next row. And then irradiance from the sun and circumsolar region of the sky for angles of incidence less than 90 degrees. And again, to calculate the diffuse irradiance for the backside, we're summing, we're dividing the field of view into 180 1-degree segments, and then iterating over that and calculating the irradiance for each segment, and then adding that together. This model makes a few assumptions that I'd just like to highlight. So we're assuming that your PV array is laid out in rows or in a row or multiple rows of modules. So I think that's fairly obvious, but you're not going to be mounting a PV or a bifacial PV module like on a flat rooftop, because you're not going to be getting anything out of the rear side. So we're assuming a row layout. We're assuming isotropic radiation for the calculation of configuration factors, so we're not assuming any variation in radiation at different angles of incidence. For the SAM implementation of this model and the base model presented in the paper, it assumes that the bifacial modules have no irradiation variation along the length of the row, which would discount edge effects. And so it's suggested that the edge effects are insignificant for PV systems with more than a dozen modules per row, though potentially for smaller systems this would be more of a concern. If anything, the irradiation on the edge will be higher, and so this model would tend to be slightly more conservative than fully accounting for all of the edge effects. And then within SAM, once we calculate the plane of array rear side irradiance weighted by the bifacial factor or bifaciality, we add that to the front side irradiance and then convert to DC power using a single diode model. Within SAM, you access the bifacial modules through the detailed photovoltaic model, and the red box highlights which module models the bifacial model is hooked up for. And so I'll go through what these inputs are. They're fairly minimal, but on each of these pages, each of these module models that are supported, there is a bifacial specifications box. And the specifications that are required are, again, fairly minimal. You need the transmission fraction, which is a fraction between 0 and 1, specifying the percentage of array row area, including through the modules, that allows light to transmit through from front to rear. Now, this particular factor we realize isn't going to be something that is necessarily easy to obtain, and so we have tried to provide a reasonable default from the model developers, but it's something that you could, calculate. The bifaciality, or also known as the bifacial factor, is a fraction between 0 and 1, specifying the relative efficiency of the rear side compared to the front side. Most bifacial module datasheets have that information. Some of them don't, but it's a fairly common and well understood factor for bifacial modules. And then the ground clearance height is another important parameter that previously has not been required in SAM, so we have you enter it here. And it's the height from the ground to the bottom of the PV module. And if you have a system that has a tracker, this would be the height at 0-degree tilt angle. As I mentioned, we are assuming a row layout, and so it's very important for you to tell us what the geometry of your rows look like. And so on the shading and layout page in SAM, you will want to specify self-shading so we can properly calculate the self-shading of the front side, and then make sure that you lay out the number of modules along the side of the row and along the bottom of the row. And given your specification of the ground coverage ratio from the system design page, that will give us the row spacing and the geometric factors that we need in order to calculate the rear side irradiance. So now that I've discussed the inputs to the SAM model, I'll go through some of the outputs. So the main outputs of interest for the bifacial model will be the bifacial irradiance gain. So that's really what the model is calculating. So in the top here, you can see the loss diagram, or part of the loss diagram has been updated to indicate the boost to nominal POA that you get from a bifacial module, and in this case, it's about 16%. And then we're also providing time series outputs for the front and rear side irradiance for each subarray, and then also the total system. And so the blue time series values here in the bottom plot, that's the front side total radiation, and then the orange would be the total rear side irradiation. So given that ability to specify a few inputs, get a few extra outputs, what would you actually do with this in SAM? So I'm going to walk through a few examples and also just highlight some of the ways that you can use this model, and then we'll actually dive into SAM and dig a little deeper into modeling. So here we're going to evaluate the boost in energy production with bifacial modules compared to monofacial modules with and without tracking systems. So in this case, I've set up a system with 3 rows of 22 modules. They have a ground coverage ratio of 0.4, and so they're spaced about 8 meters from row to row at a tilt of 30 degrees, and they're about 1 meter off the ground. The ground albedo, which is a very important factor for bifacial modules, we're assuming that you're not installing your system in a highly prepared field of a very white reflective surface. So we're assuming a fairly normal field of grass or something like that with a modest albedo of about 0.2. So the results that you get using this, if we consider just a monofacial fixed tilt system, you get about 190,000 kilowatt hours of POA irradiance. And then if you instead install bifacial modules at fixed tilt, you get a boost of about 8% for both the irradiance gain and energy gain. If you instead of installing a bifacial system, install just a one-axis tracker on the monofacial system, you get quite a larger boost of about 33%, and that translates to a 26% energy gain simply because the DC energy gain is different from the irradiance gain due to nonlinearities in the module model. And then finally, if you wanted to take it to the next level, if we install bifacial modules with the one-axis tracker, you get an even greater boost, ending up with about a 33% boost in DC power or DC energy. And so what that says for this particular scenario is that depending on the relative cost of a bifacial module relative to adding a tracker, you're going to potentially get more energy out of installing a tracker. But again, it's the main point of any of these trade-offs would be to provide more value to the system. And so I'm not a cost modeling expert for tracking systems or for bifacial. And so it really comes down to figuring out what is the cost of installing a tracker versus what is the cost of installing bifacial. And it'll be different for every system. But it's the kind of analysis that you can very easily do in SAM. There are some key variables that go into designing the layout of the bifacial system. And so, as I mentioned before, the ground clearance height is an input for the bifacial model. And in the plot on the top left here, you can see that we're varying the ground clearance height from about 0.5 meter to 5 meters. And you can see sharp increase in the annual energy produced as we increase the ground clearance height up to a certain point where it starts to level off. And this is because as we increase the ground clearance height, we're able to capture more ground reflection. And so it's a fairly strong driver. Another strong driver would be the ground coverage ratio, which would be as we start to space the modules out more or less, we're able to capture more reflections from the ground or from the rear side. And so you can see as we start at a fairly low GCR, which would mean large row-to-row spacing, that's kind of where we're maximizing the annual energy. And then as we start cramming the panels closer together, we're starting to drop off in the bifacial irradiance gain and the annual energy produced. And so I produced both of these plots using the SAM Parametric Tool, which I will demonstrate here in very shortly. Another thing that you might want to do is just completely optimize your layout, varying many different parameters. And so in this case, I've varied the ground coverage ratio from 0.1 to 0.5, the tilt from 15 to 45 degrees, and the ground clearance from 0 to 2 meters. And then I've sorted by annual energy. And so this is essentially trying to optimize the layout of the bifacial system. And so what the results here demonstrate is that you're going to achieve the highest gain when you, again, increase the ground clearance height, reduce the ground coverage ratio. In this case, a tilt of 40 degrees is the one that produces the greatest annual energy. And so this is a really quick way to start looking at those sensitivities. And so with that, let me actually jump into SAM, and we can start more clearly illustrating how you would do this yourself. Just 1 second, we'll get set up with SAM here. All right, so what I've opened here is the beta version that is linked to in the PowerPoint presentation. So I'm going to go to the photovoltaic detailed tab, and I'm going to go ahead and start a commercial system. I'm just going to go ahead and leave the default location selected, which is Phoenix. And then I'd like to point out here the albedo input. So by default, we provide a monthly albedo input that you can update, and we provide a default of 0.2. You can also, if you have Timeseries albedo available in your weather file, you can use that here. For now, let's assume that we are going to have a slightly higher albedo. So let's assume that there's some different tables that you can look up for albedo, but essentially as you make a white surface or a more polished surface, there's some films that increase the albedo. But let's assume that we have a pretty high albedo of about 0.5. For the module page, this is where we activate the bifacial model. I'm going to go ahead and leave the default module selected and then just enter this checkbox for modules are bifacial. It's possible that before the release, we'll also hook up the ability to detect within the CEC database which modules are bifacial and then check these automatically. So I don't currently have that hooked up, but that is something that we would like to do. I'll go ahead and leave these as default, assuming that the rear side can convert electricity at efficiency of about 65% relative to the front side. For the inverter, I'm going to go ahead and just leave the default inverter selected. On the system design page, I'm going to specify a system of about 200 kilowatts with a DC to AC ratio of 1.2. And I'm going to start with a fixed tilt system, and I'm going to go ahead and leave the default tilt of 20 degrees and the default ground coverage ratio of 0.3. So the next step that I'll need to do is set up the row layout. So basically, how does this system lay out? And as I mentioned, we'll want to enable self-shading so we can properly calculate the shading on the front side of these rows. And then Sam is warning me that the number of rows in the subarray, in subarray 1 is not an integer, and that's something that we can easily fix. So if I go to the system design page, we can see that Sam has automatically laid out 6 modules per string. And right now we have 7 modules in the bottom of the row. And so we just need to make this a multiple of 6. And so we'll assume that we just have 18 modules in one row, just one up. And again, this is just a demo, so I mean, for a real system, you would have your design criteria that you'd be trying to meet. And so Sam automatically calculates 33 rows. The length of each side is 1.6 meters. And then the row spacing is about 5.5 meters. We'll leave the default module aspect ratio detected. Again, the CEC database now has some information about module geometry, which we would like to incorporate, but currently this is something that you can modify. For the rest of the configuration, we're going to leave everything as default, so we're not going to specify any additional losses or a battery. For the system costs, I would just comment here that, again, for bifacial modules, I'm not a bifacial module cost expert, but you could update any additional module costs that are different from a monofacial here in the system cost page. And we will leave everything else default. And so let's just go ahead and see what results Sam comes up with. So a really quick way to see what kind of gain we're getting is to go to the loss diagram, and we can really quickly see that we're getting a gain of about 15 to 16% nominal POA for our array. So that seems, pretty good. So let's compare what we're getting to a monofacial just to see if there's any other subtleties that we might want to investigate. So with the bifacial module, we're getting about 420,000 kilowatt hours of annual energy produced. With a monofacial system, I just have to go back to the module page and unclick this. We're getting about 370,000 kilowatt hours. So we're getting about a 50,000 kilowatt hour boost. So we can just do a really quick calculation. So 50 divided by 370, we're getting, about a 13.5% annual AC energy gain. Now, one reason why we might be getting a slightly lower annual energy gain, AC energy gain, than this 15.8% here, would be that for bifacial modules, we are sending more power through the inverter. And so if your inverter is, we've specified a 1.2 DC to AC ratio. And so it's possible that some additional power could be getting clipped for the bifacial system, since when we size the system using this DC to AC ratio, we're not considering the radiation from the rear side when we size this system. So that's just one caveat to note. So now that we have seen just the difference between monofacial and bifacial for this fixed tilt system, let's take a look at if we can make it even better by optimizing some of the inputs. So I went to the parametric tool in the bottom here. I'm going to add a couple of the key variables of interest. So if I start typing ground, I'm going to click the ground coverage ratio, which dictates the row-to-row spacing. I'm going to click the ground clearance height using the CEC database module model, which is what we're using. And then I am also going to type tilt, and I'm going to select tilt 1. And within the parametric tool, if you see these tilt 1, tilt 2, tilt 3, tilt 4, that simply refers to the different subarray options in SAM. So you can specify up to 4 subarrays. Typically, you would do that if you had one part of your system that is faced, has a different tilt or is faced in a slightly different direction. That allows you to configure those kind of variations within your system. Right now, we're just using one subarray, and so we're just going to vary tilt 1. So now I have these three different inputs that we're going to be modifying. So we can really quickly define the ranges. So for ground clearance height, let's just say 0, 4, in increments of 1. For ground coverage ratio, let's do 0.1 to 0.6. And recall, the ground coverage ratio is the inverse of the row-to-row spacing. And so as we decrease the ground coverage ratio, we're increasing the spacing. And we'll make it increment in 0.1. And then for the tilt, let's go between 15 and 50 degrees in increments of 5. And so this is going to give us 240 simulations. And the reason why it's so many is because we're looking at every single combination of these three factors. And it's telling me that I need some outputs to generate along with these. And so, again, the items of interest, let's take a look at the rear side bifacial gain for the POA. And then let's also look at the annual energy. So while this is generating, I can discuss a little bit of what's happening here. So essentially, we're going to take that parametric table that we've input and prepare SAM, and then run 240 simulations that we'll give back to you. And the great thing about this is it allows you to fairly quickly optimize your system through lots of different combinations of variables for using a model that's fairly complex. And so to calculate the rear side irradiance for the bifacial module is a fairly complicated geometrical problem, but we can easily look at many variations of it using this model because it runs very fast thanks to the design of the people who made the model. And so I think it's a pretty neat way to look at how these systems interact with different design parameters and give you a quick picture of what are really the key drivers for these systems. So we'll just wait. It should be done in just a few seconds. Okay, great. So we have this large number of outputs. And by default, the results that SAM presents aren't, necessarily that helpful since there's so many of them. But you can see some clear peaks and valleys here within the system design. And so the way that I usually like to look at this is use this export function on the top right here and then send to Excel. And I think I made it a little too big this time. I think I can just copy it to the clipboard. And then within Excel, I like to sort the data on one of the output columns of interest. So let's take a look at the annual energy. And we'll make it largest to smallest. Expand everything. And so this is going to tell us what combination of these variables results in the optimum system design. And so SAM is telling us that if we put our modules at 4 meters standoff, which again is very high, so you probably wouldn't actually put them that high, but SAM is telling us that that is the ideal height. You'd make them very, very spaced. A tilt of 35 degrees in this case is going to produce the most annual energy. And we're going to get a bifacial gain of about 23% or 23.5%. And so that's that's quite a boost over our initial 15 or 16%, but it comes at the cost of having to have more land. So decreasing the ground coverage ratio is going to mean that we can put less modules per acre in our installation, and so that might be something that you simply can't do. And again, this 4 meter standoff height is probably something that you're not going to necessarily do. But it gives you kind of a big list of design options to choose from, and shows a few different options. And so that's one additional thing that we could look at. Another item that we might want to look at is, again, the tracking option. And so what is the trade-off between going from a monofacial system that is fixed tilt to a monofacial system that is a one-axis tracker to a bifacial system that is a one-axis tracker? And again, we can very easily do that in SAM. Just duplicate the case. Go to the system design page. Turn on one axis. And so now we're getting about 477,000 kilowatt hours of AC energy. And that is again compared to 370. So we're getting, quite a large boost there. If we were to add a one-axis tracker to the bifacial, we're going to get still more. And so again, this is a fairly powerful way to evaluate different system design options, but ultimately you probably you don't care as much about the annual energy. You care about the LCOE and you care about the net present value to your project. And again, that is where cost modeling comes in. So moving from bifacial or from monofacial to bifacial, there is presumably some difference in cost that needs to be defined and understood. There is some additional manufacturing processes that happen for bifacial modules. It's not quite as simple as just removing the back sheet. And then there's cost differences between between going to bifacial and then adding a one-axis tracker. And so we've been primarily looking at the annual energy for this demo, but again, in reality, you're going to care about the value to the project and whether or not it's worth it for you to incur additional costs and whether or not you get the value back. So again, that's just a pitch for having a solid understanding of the differences in costs between these technologies and the additional complexity that requires. And with that, I know we still have about 20 minutes left, but that's pretty much all that I have to demo for you today. So I would definitely welcome any questions that you have or feedback. So I guess we can just open it up.
Great, thanks, Nick. We got a lot of questions in the questions box during the webinar, so I've been writing some down to address. And then we can go through more because I'm sure more will be coming in. One question to start with is we had someone wondering when the bifacial model will be available in the software development kit or SDK.
Yeah, that's a great question. The SDK is a product used by companies or researchers who want to wrap SAM in their own workflow and essentially add more complexity. So it can serve as the back end to a lot of companies' workflow. And we've definitely had a lot of interest in the bifacial module for the SDK. There is the beta version available. So let me go ahead and open up this PowerPoint presentation again. And I'll just rest here for now so you can copy this down if you'd like.
And Nick, I also put the links in the chat box, so they're available there as well.
Oh, thank you, Paul. So yeah, the SAM SDK beta is available, and then we will be releasing the official public release in September along with the desktop application.
Great. Another question that came in is whether the DC to AC ratio on the system design page of SAM represents just the front side rating for bifacial modules, or whether it also takes into account the power, or the rated power, including the rear side irradiance.
Yeah, that's a great question. So on the system design page, when you specify the DC to AC ratio, that is only considering the nominal capacity of the front side. And we could potentially consider a way to try to consider the rear side. The main challenge there is that the power produced by the rear side is highly dependent on the system configuration. And so even on module manufacturers' data sheets, you don't always see like a nominal capacity for the rear side, since it's so dependent on the albedo of the ground and how the rows are laid out. And so there's really no clear way to take a nominal module, for instance, of 335 watts on the front side, and then say that it's a nominal power of 200 watts on the rear side, for instance, since it's just so layout dependent. And so what I would do is, when you are sizing your system, just try to take into account the fact that you're going to need to reduce this DC to AC ratio so you have enough inverter capacity for any production that's generated by the rear side. And you should be able to pretty quickly see if it's a problem or not if you look at the loss diagram. And if you look at the AC inverter power clipping loss, you'll see that in this case it's about 3%, which isn't too egregious. But if we go to the bifacial one axis, we can see it's still only about, it went up a little bit, but not a ton. And so this tells me that the system is not being highly limited by the inverter. But if you saw that this was jumping up to like 10% or 15%, then you'd really want to consider adding some more inverter capacity. But yeah, that's a great question.
We're also getting a lot of questions on mismatch losses, with the backstory being that the irradiance is not always uniform across the rear side of a bifacial module. So there are some questions for whether or not those mismatch losses are accounted for in this model, and perhaps a little clarity because there is a mismatch output in the loss diagram.
Yeah, that is also a great question. The underlying model that we've used for the bifacial irradiance model, since it's only calculating the irradiance on the rear side, that particular model does not get into any mismatch issues, and we have not considered them at a first pass here. We certainly do acknowledge that they should be accounted for at some point, but we have not yet done so. And so I believe I'm not 100% sure, but I think that there are some proposals and work going forward over the next few years to investigate what that effect looks like and how to model it, but we don't currently have the model for it. Regarding the existing mismatch output in SAM, which I believe, can't remember if it's on the losses page. Yes, so this module mismatch percentage right here, I believe this accounts for module mismatch between subarrays, or within a subarray, and so it's a point loss that you can specify, and this would be an example of a place where if you knew what the bifacial mismatch was, you could add to this, but we don't currently have a model for it.
And then a follow-up question was if you could specify mismatch specifically for the backside, which as Nick mentioned, you might be able to enter in the mismatch loss here, but related to that, there was a question for whether or not you can specify a separate soiling loss for the rear side irradiance, and that related to that, whether the bifacial irradiance is calculated after soiling is applied to the front side irradiance. So if effectively if it includes soiling or not on the rear side irradiance calculation.
Yeah, those are all great questions. Right now, you cannot currently specify soiling specifically for the rear side, though I would hazard to say that we still haven't completely figured out soiling on the front side, and so it might be a little while before there's rear side soiling effects considered, but absolutely we could see how that would be a valuable place to derate just the component of irradiance coming from the rear side. The way that the model flow works is the front side irradiance is calculated, so all of the shading and soiling losses are applied to the front side, and then that derated front side irradiance component is then used as the input for the bifacial calculation. And so the bifacial calculation essentially is, again, going through those various segments and iterations, and then computing the various contributions from the ground, from the front side of the next row, and so on. But it does come after the calculation of all of the losses on the front side.
We have another series of questions from several people, basically on whether or not you can model the impact of mounting structures on the rear side irradiance, so shading from those on the rear side of modules.
Yeah, I mean, you can certainly envision like certain mounting configurations where you would be losing a lot of the irradiance. And right now we do not consider any of those effects. We consider that you have a very minimal rack system and that it's not blocking the rear side. I believe for a more complex consideration of those kind of effects, you'd almost have to go to a ray tracing algorithm, which is something that the model developers at NREL and Sandia have done, and they have some pretty complex models developed, and they used those models to evaluate different systems, and I believe ultimately used it as a support for deriving this this slightly simpler model. But yeah, that's a great question, and could potentially derate the amount of bifacial irradiance by a few percent, depending on how bad the blockage was.
Maybe also worth noting why we chose this simpler version instead of the ray tracing based model that was also developed for implementation in SAM.
Absolutely. So the ray tracing approach is great because it considers every single ray of light and how it bounces around the whole system and is absorbed by the active surface. But it comes at a cost of computational complexity and runtime. And so for SAM, we wouldn't want you to be sitting waiting for SAM for like several hours just for one simulation to finish. We tend to implement models that can be run in a few seconds to maybe a minute or two at the most. But we also want those to be accurate models, which is why the teams that have developed the models typically start with something like a ray tracing algorithm or a more computationally intensive approach, and then try to reduce it to a simpler approach that is still, fairly, that gives results that are still satisfactory for a generalized system. And so we believe that this is a great approach for SAM and provides with users a lot of flexibility. As you saw, we ran about 250 simulations in less than a minute. And that's kind of where we envision the power of SAM and this model.
Great, thank you. Don't worry, there's still more questions coming in. Good thing you left so much time for them. There was a question on whether or not you know of any field validation of these models or comparisons to PV-cyst, which I know Nick noted that we are not the developers of the model, but are at least passingly familiar with the work that's gone into developing them.
Yeah, absolutely. I know of at least a few people that have either ongoing studies comparing different bifacial models or have plans to do so. I can say that some of the results of this model as implemented in SAM have been compared both to the bifacial VF code that I linked to, which is the raw Python implementation, as well as PV-cyst and a few other models. And again, I'm not the primary author of those, so I can't share those results right now, but needless to say, we have a lot of people interested in that, and of course PV-cyst is a very popular tool, and so we want to make sure that we have some alignment or understanding of going towards a common ground in bifacial modeling. But I would presume that those results and comparisons will be published at some point in the near future. But yeah, I'll have to, if you're interested, I can certainly put people into contact with people that would know more.
And we can also, on our performance model documentation page on the SAM website, we can post some links to the original formulations of these models and maybe some of the validation studies as well for people that are curious about the model in SAM. There is a question if there are any plans to implement the bifacial model with two-axis trackers.
Yeah, that's a great question. Right now, you could actually run the bifacial model with two-axis trackers, though the complexity starts to get into whether or not the shading is being correctly calculated on the rear side at that point. And so I'm not totally sure how well the model scales to those two-axis tracking situations. That is definitely an area that I will try to investigate a little more before the release. But right now, there's nothing stopping you from clicking two-axis tracking. The question is whether or not those trackers are going to be doing anything terribly useful for the bifacial model because they're optimized for the front side irradiance. So just as an example, let's see so we go to 554,000 kilowatt hours. And again, that's compared to 510. And so you can see there's definitely still some boost that is occurring. Again, most of the tracking algorithms in SAM were developed with just the front side in mind, but there are certainly companies and research that is going into optimizing tracking algorithms for bifacial models or bifacial modules, but we have not implemented those.
Great. There's a question on whether or not we know of any sources of time series albedo data. I believe that the latest version of the NREL National Solar Radiation Database can provide time series albedo information for different locations. That covers most of North America and a good chunk of South America in that data. However, it should be used with caution because the albedo has such a large effect on the output of bifacial modules, and the albedo is still a modeled output for different locations in that data set. So within a 4 kilometer by 4 kilometer grid cell, you are still going to experience a decent amount of variation in what the albedo is, depending on the exact surface that you're installing your system. So if you are installing your system in a field, then your albedo variation is going to be different than, even within that same 4 kilometer by 4 kilometer cell, going to be different than a building located there as well. So that would be the caution for that. Frequently, someone who would be looking at that level of detail in albedo time series data probably is performing some type of pre-construction measurement campaign at their site using an albedometer installed at the location. So that's probably more of what we envision people using that time series albedo input for. There was a question as far as which point on the rear side of the module is the irradiance calculated at? Is it in the middle or the top or the bottom of the module?
Good question. So the model actually considers 6 rows along the rear side. So as you go from the lowest part near the ground up towards the highest part, it's divided into 6 rows along that rear side. And so the rear side irradiance is calculated for each of those 6 rows, and then we take I think we take the average value of that.
Okay. With about 2 minutes left in the webinar, there's still a couple more questions. I will mention one real quickly. There was a question for whether the bifacial model is going to be available in just the commercial model, and the answer is it will be available in the detailed photovoltaic model, meaning that it's available with any of the financial models that can be coupled with the detail PV model, which is all of them. So it will be available for commercial, for utility scale, even for residential, although residential bifacial PV is at this point probably fairly unlikely. And then maybe one more question. Have you looked at all at the impact of backtracking on that bifacial gain when you're considering one-axis tracking systems?
We have certainly used the bifacial or the backtracking. And of course, with backtracking, the idea would be that you are trying to eliminate all self-shading. And so we can quickly, that is another feature that I could have highlighted. But yeah, the backtracking algorithm certainly is available to use with this model, though it is still only considering the front side irradiance. And so it's going to be trying to reduce all of the shading on the front side, which may be a positive effect for the rear side, but it's not specifically tied to trying to increase the rear side irradiance. And so you can see we have about 518,000 kilowatt hours with backtracking. And sorry, let's also really quickly look at the bifacial gain. So this is about 11%. And if we move back to no backtracking, you can see that it did provide, some very small boost to the bifacial gain on the rear side, but the main benefit would be to reduce the shading on the front side. So, but yeah, at that point, I guess we have reached the end of our hour. We appreciate all of the great questions. And again, as you download this model and start to play with it, please let us know if you see any issues. And yeah, we'll definitely look forward to hearing the feedback.
And if you have other questions, feel free to join us for one of the SAM roundtables where you can ask the team live questions on the model as well.
So yeah, with that, we'll go ahead and end the webinar, and these slides and recording will be available either sometime in the next day or so on sam.nrel.gov/webinars. And thank you again.